Okay, let's try an example here, adopting what we have learned in the previous two slides. So here's an examples. You have a 600 meters diameter pile driven to clayey soils. You have a knot. So you have again you have a piles right there. The difference into the clay soils. We know that this. So if this going driving downward, so if the frictions pointing upward, and the total frictions for this piles is 500 kilonewtons. And you have a nominal lead toe bearing capacity. At the bottoms is 500 kilonewtons, and it asks you to develop two settlement curve. One is the side frictions, so this is the side frictions, and this is the toe bearing. Again, like for piles, the settlement of piles depends on the loading. So it's not one like a magic number. How much settlements? You have different components. You have the elastic compressions. You have the side frictions. You have the toe bearing. So here, we is only ask the side frictions and the toe bearing. It didn't ask you the elastic compressions, and also those settlements. Each of the three components depends on the pilot loading, and or how much loading has been mobilized, or the loading mobilizing the displacements. And also we know the undrained shear strength of the soil at the bottom. So here the clay here is the strength is 100 kilopascal. Okay, so first, we look at the side frictions. We know that the formulas that we have previously involve a Ks term. So the Ks equals to ms times the diameters of the foundations, and then times the total frictions. And if we plug in the numbers, so ms for this case for clay soils and the piles is 0.004. You can reference the previous slide for the table. And then the diameter is 0.6 meter, and the total friction force is 500 kilonewtons. And remember the equations from the model we learned previously. So is the side frictions equals to the displacements at the side. So that's why it depends on the displacements, the loading, and the displacements. They interact with each other. And this is a constant case S that we calculate. And again, the side frictions, and then the nominal frictions. So those are variable. So this is a variable, loading and displacements, and the rest is constants. And if we plug in the numbers, it will be this again. And case of S is whatever you calculate here. It's a constant. And the F and AS, the nominal side frictions, is 500 kilonewtons. So this is equals to the loading. So pretty much this is the equations that we are looking for to describe the settlement curve for the side frictions. So if you plot this up, which is this curve here, and pretty much like this is your y-axis, this is low, and this is your x, and this is x variable. So it's a hyperbolic curve that we discussed about before. So this is the side frictions, and also we can do a similar exercise for the toe bearing. And the toe bearing require like terms of E25. So according to the method we discussed above, is equals to 825 times the SU values, the engineering shear strength of the clay at the bottoms is given at 100 kilopascal. So we've multiplied the two, we get 825 and then 100 kilopascal. That's E25. And the model need a constant term called K sub T equals 0.54 divided by E25 times the diameters of the piles. And if we plug in a number, this is equals 1.09 times 10 to the negative 6. And the formulations again is a hyperbolic models equals the toe bearing loading equals to the displacement at the toe times the constant that we just calculate, and then plus the displacement at the toe again divided by the nominal toe bearing capacity, which is 500 kilonewtons again. So we know this constants, and again this become like equations to describe the displacements. So very similar. So this will be your y term again, this is your x terms, this is your x terms, and this equations that you got will be represented by this graph here. So this is only like two components of the total settlements. You still need to find out the elastic compressions that we talked about previously with these equations. Then you add up the three components, then that will be your total settlements. And again, this total settlements will be represented by a curve. So here I just want to break down like how we approach pile settlements issue. Is complicated because now is a stress strain relations of these piles, soil reactions, interactions phenomenon. So it's kind of like, it's no longer one dimensional. Everything is two dimensional. The total settlements depends on the loading. And again, you have three components. So I want to break it down and then make use of one hyperbolic model, the Chin's hyperbolic models, the Cook 2009 method, to walk you through the math behind, and also hopefully helps you to visualize indeed is a curve. It is not just like a one single number when you calculate the settlements, and the curve is describe the response between the loading and the settlements. Next we talk about DZ method, which is more a comprehensive engineering approach to tackle problem like this, and it's more popular to use the TZ method in practice than this hyperbolic models. But the hyperbolic introduce you to hyperbolic models, hope to help you to visualize what really happens going on behind the scenes. Okay, next is talk about the TZ method. So the TZ method is a very advanced engineering analysis method, and I saved this as the last of the course. I just want to bring you guys up to the next level, more try to look at the design of a more complicated problem like we are doing now, the settlement or the displacements of deep foundations, the long piles. And it just again is complicated because you have like three components, and at least two of them involve soil structure, which means the soil pile interactions. And it's complicated in a way that not doing like a single material, and it's not just like a scenario at a time. You have three different components. Again, pile settlements involve the elastic compressions of the piles, the side frictions settlements, and also the toe pile toe settlements, and each of them depends on the loading. So this is a complicated phenomenon, and there's kind of like a genius, Calf, come up with a method. Calf et al. 1981. What he do is like he mimic the soil pile response, the soil structure response, by like a spring, actually a series of spring. So a picture to capture the TZ method, a good one will be here. So you pretty much like summarize what is the simulations we are trying to do here now. Is again, we have three different like component of settlements, right? First, the elastic compressions. Seconds, the elastic compressions. Pretty much you use the pile spring here. Second is the side frictions. So this is the first one. The second one is the side frictions or side settlements. And he used like a spring, like F's. Usually we call this like a FZ spring, and finally he also has the toe settlements. So the toe displacements. Then he has another spring. So he has like a three set of springs, and like the side frictions and the pile spring. You have a series of it, because another like philosophy he has is he break down the long piles in different segments, and kind of like a working backward, and kind of like a little bit like a finite element approach. He solved the problem like element by elements, and chop the informations in pieces, and then like you can pass on the distributions of the loading and also the displacements. Anyways, so you have three different spring here, or different set of springs over there. You have a series of internal like elastic compression spring. You have the side friction springs, and also you have the toe, the spring, one spring at the toe. Usually we call this to be QZ spring. So the why you call this as a TZ method? Actually, the side frictions they are usually called the TZ spring. So this is the TZ, this is the QZ. So we have so called it the TZ method is because part of it is we use TZ to represent the soil spring at the side of the pile. So this is another like a picture of what really going on. So you have a series of spring. You have the spring represent the stiffness of the piles or the foundations, and also we have the spring representing the side frictions resistance. So we know soil has resistance or stiffness. Remember, like the consolidations theory we learned from Terzaghi. Terzaghi also used a spring analogy to describe the consolidations like a response. So same here, like the soil pile response. Calf he used like a series of spring to mimic that, and also we have a spring representing the toe bearing resistance. We only have one spring for that, and this series of spring here at the middle, those are the elastic compressions. So tightly depends on the Young modulus of the piles. You have steel, then you use the Young modulus of steels. If you have concrete, then you use the concrete with reinforcements. Then we have calculated that before in the previous lecture. Then you have the modulus value for the concrete and steel combinations using the ratios between the two. And finally, we also have the TZ spring. So all these are the TZ spring right there, and the TC like a response is represented by a curve. So same here, you will have the also have a curve to represent the spring. Usually we call this a QZ curve, the QC spring. And the spring to represent the stiffness of the foundation, since this is like just a material, one single material only. So the Young modulus typically can capture it. So this will be captured by the modulus, the Young modulus of the material, the modulus of the pile. So that's the setup of the TZ method, and if we work at examples, I think you will make much better demonstrations on how this method works. So again, there's three components. We have the three components, which is the toe bearing, the side frictions, and the elastic compressions. And to capture those two responses, the toe bearing, we have the QZ curve. The side frictions is a TZ curve. And to capture the elastic compressions of the piles, we use the Young modulus. So those are the three input informations you need to have. Okay, so this flow chart here shows the analysis of TZ method. And if you're coding it in computer, language, MATLAB, or Python, a flow chart like this will really help for you to write the loops. And the whole idea or the big picture here is, again, you will divide your piles in different segments, and then you work through the pile from the bottommost to the topmost. With that, then you can from each segments you can calculate the displacements and loading, and give you a good idea on how the piles look like in terms of the load distributions and displacements along the piles. So that's the flow chart, and I think it will make more sense if we try to do an examples together. And I have uploaded this spreadsheet to Canvax, so you should be able to find this. So let's look at this example together on how this works. So first, before we do anything, we need to have a couple informations ready, or make an assumptions on certain materials or certain parameters. First, we need to assume Q max. Oops. So that is the maximum toe bearing capacity at the toe, and we need, so after we have the Q max and also the F max, so both the side frictions and also the maximum side frictions and also the toe bearing capacity. So you can evaluate those, actually the Q max and F max. So just like lecture number 5, right? If you evaluate the pile capacity using alpha, beta, or alpha method or beta method, then you can find out the side friction capacity and also the toe bearing capacity for the pile. So that's just Q max and F max. So those you're using an analytical approach in lecture 5. So again, this not assume, maybe calculate. So this would be lecture 5. the Q max and F max. Then after that, you need to have those. This is like the QZ curve ready, and also the TC curve. So this is the toe bearing displacement curve and the sine frictions displacement curve. Those are normalized curve. So that's why you need to have the Q max and F max, because like you have like this ratios multiplied by like the Q max for your piles, then everything go back to the loading for your piles. So likewise, you need to also have the TC curve. And this too can come from like literature, based on literature. So past research have done some research work to tell you how the shape of the displacement curve look like. And I upload one reference to CanFact, so you should be able to see this. So this one is showing you the this is the TZ curve. So pretty much like this is the side frictions normalized by. So this is a ratio. So this is the maximum right there, maximum side friction. So if you have your own F max for your piles, so you multiply by that number, then like you change that to loading, and then that represent your piles. But what here is dictate the shape, the shape of the piles, and it comes with a range. So at the beginning, I think as a beginner, I recommend that you take the average. After you have more like experience, then you know when to take the upper range, based on the salt type, also based on the structure. So but at this point, you can take the medium like a curve. So that represents your TZ curve. So likewise, this is the QZ curve. So this is based on drill shaft in clay, and these strongly also dictated by the type of foundations. Those are the drill shafts, and this is like also the drill shaft for sand. If you have a piles, then you have a different kind of curve. So this is only for the drill shaft. So you realize the sand curve versus the clay curve, you can have significant difference. So and those dictates like the shape of a curve, and you need to find your own Q max and F max to apply to that. And the x-axis is the settlements normalized by the diameters. So this the B sub B right there is the diameters of your piles. So they this come from research work, so they have come up with this kind of like a template, or like typical the shape of the TC and QC curve handy for you apply to your for practitioners to apply for the structures of the projects to be used. So the x-axis is the kind of like the settlements, right, but normalized by the diameter of the piles. The y-axis is the loading. So either normalized by the maximum toe capacity or the sine frictions like a capacity. If you find out your own Fx or Qmax values, then you can convert that back to the loading that for your own project. So before we do the QC and the TC, before we do the TC method analysis, we need to have those ready. So now we have like those three pieces of information ready, then we can start our TZ analysis. So pretty much this is all this example here. So this is all the background. So this piles, the examples here, what they do is we try to break down our piles into 4 parts, into 4 segments. And the whole piles is 200 feet long, so you break down to every 50 feet, and the midpoint of the first segment here is 25 feet, and here is 75, and this is 125, and this is 175. And we will need the TC and QC curve. So for this exercise, this is a simplified example. So we try to use a very simple TZ curve and QC curve over here. Instead of a curve that you're seeing, we even oversimplify the curve in like a perfectly elastic and perfectly plastic material. So this just like a two parts. So it'll be easier on the computer coding we do on Excel. But like you can also read off from the curve for your own exercise. Actually, for your own homework, you can just read off the curve instead of like coding the whole curve in your Excel spreadsheet. That because if you have the non-linear part, it could be quite complicated to do that. But we take advantage of this as a simple curve, so we can still code it in the Excel spreadsheet. But anyways, so we have already calculated the Q max for the curve here. So this is the Q max, 95 kips for this like so here is the Q max, 95 kips, and we know the diameter is like a 36 inch. The thickness of the piles is like a 0.75. So and this is calculated area. So this is a hollow pipe. So hollow steel pipe. So we know so we know the thickness here, which is 0.75, and also we know the diameters of the piles. And so that's why we need to calculate the area. I let you think of the math, just the geometry. And also we know the stiffness, the elastic modulus of the piles of the steel here. So it's KSI, 29,000 KSI for this piles. We need this information to calculate the elastic compressions, and the whole length again is 200 feet. And we also have the QZ and TZ curve, and pretty much this is the coding that we use for the QC, and then this is the TZ. So pretty much like all this coding here, all this just representing this graph, the QC and also the TC. So that's what this two parts do. And also we need the side fictions, and the side fictions, the fx maximum values, right? And like we have it here. We have it here. And it's just the side fictions is functions of the area, the side area, the length. So that's why like at different depth we have different like maximum side fictions values. Okay, so the whole idea here now is like is to work back work. So we have elements 1, 2, 3, 4. So this is element 1, 2, 3, and 4. So we start with the very last elements, element 4, and the depth at the center of the element 4 is 175 feet deep, and the length of the piles. So actually we should look at this, right? So the length of the so kind of like we work with back work. So this is kind of like if we do the analysis from scratch, this is what we have. We try to work from cell to cell to cell. So so this what I will start, like from up to down and from the left to right. So so this is again, we look at element number 4. We are at the depth of 175 feet. The length of this segment is 50 feet, and then like the first thing to do, the very first thing to do is calculate the stiffness. So the first step here is to calculate K equals to the Young modulus times the area divided by the length. So this is what we do here, and we have all those informations already. So we know the stiffness of the piles, And then next is we assume the base settlements and the start of the loading, and we will put this equal to 0. So that's why like this is 0, and we assume this one. So this parameters means like the base settlements, the settlement at the toe, and we need to assume this number. We assume this is 0.005. So pretty much this one. If we change this, I think we change a little bit. So, but like at the end of the day, you shouldn't change much on our results. But like we assume this number for us to start. Then we can calculate the loading, or find out the loading. So this is the loading at the toe, and pretty much like the coding here I have here is just width from the curve. So because pretty much this is the QC curve we talk about. So here we assume a settlements of 0.05 inch. So what we do here is like we assume this 0.05 inch. We know this is 0.05 inch. Here we find 0.05 inch, and then we go to this curve. Whatever we read, that will be my my values, my Qmax values, based on this like displacements. So pretty much it's just read off this curve, and then you need to multiply by the Qmax. So what we'll be doing here, this part will be the Qmax that we know times whatever we read from the so this times the values. So the Q over Q max curve, right? Versus the settlements, and this case we know this is 0.75. So we read off this curve, and then we go here. So whatever we read from this curve times the Q max will be equals to this number. That's what we do. And then next we take the average between this number to this number, because we are working on segment number 4, right? We'll use segment number 4. So here is the PB that we read off from a QZ curve, and this one is this one, column E here, the PD where we start. And then like here now we try to calculate the average between these 2 points. So this is the average. So you realize this number will be the half between like the PB here and also the PT start. So after we know this, then we can so that's the step number 4 is to find the average. Then after that, we can find out the settlements. The average settlements will be equals to, or the settlements at the midpoint of the elements. So it will be the average that we just calculate divided by the modulus. So pretty much this is the elastic compressions, right? And then like what we will do. So this is the elastic compressions at the midpoint. Then after that, we will calculate the whole settlements, or the settlements at the top. So here means like the settlement at the top right here will be equals to the elastic compressions plus the base. So that's what we try to calculate. So it will be equals to the base settlements plus the elastic compression settlements. And after that, we'll calculate the side friction settlements. Will be equals to the base settlements plus the elastic compressions divided by 2. So we want to calculate the settlements at the middles now. So we calculate settlement at the top. We also calculate settlement at the middles. Will be equals to the base elements plus half of the elastic compression settlements. So that's what we do. So the settlements at the midpoint. And then next, we have the fx max, right? We assume that at the beginning, and then we try to find the TC using the TC curve. So we know the maximum values, and then we try to read off the curve. Because like we know like the settlement at the side. So here, like, you know, we are reading like a 0.05 whatever again. Then we can read the TZ curve. So the next step here, what we are doing is we know the fx, the maximum. And then like what we can do is read F, the side frictions from the F over F max versus the settlement curve. So we know, like, you know, this QS here. So now, like as a side, the midpoint of the side. So this is like settlements at midpoint of the side of the piles. So we take this number, go to our TZ curve, and then have this number multiplied by F max. Then we can find our side frictions. So that's what we do here. So we get our side frictions. And then at the end of the day, we can find out, we can back calculate, or we can calculate again the loading at the top. The loading at the top will be equals to the base plus what we read here. So the loading at the base, here we already have calculated at the beginning from the QC curve, right? So we read from that, then we kind of like a loops. So at the end of the day, we go back to calculate the loading at the top. So which we go back here. So we at the beginning we assume this, right? Now you have another one that you calculate at the end, and you will compare these two numbers. That's what we do. So at the end of the day, we compare these two numbers, the one that you assume at the beginning and then the one that you calculate. make use of the TZ and QZ curve, and also elastic compressions. And also along the way, you find all the settlements. So you find, because of the TZ and QZ response, and also elastic modulus you have at the beginning, you can recover all the informations, which is all the loadings and all the settlements. And now you compare the loading at the top of the elements again, and then you find out this is different than that for your first iterations. Because like at the beginning I assume this to be 0, so this and that are got to be like a lot of difference for first iterations. So here is your first iterations, this is your second iterations, this is your third, fourth iteration, so on and so on. So what you do next is like you would take, at the end of the day, you take this number to here again, and then you do the same thing. So now at the top of loading, now you have an calculated number rather than like assume the number as 0. So this is equal to that, and then you do the whole thing again, and at the end of the day you got another numbers, and then you compare the two. Sorry, like you get another number here, and then you compare this two, you find out the difference is smaller this time. And then you would take this number and then go to here again, and then your third iterations. At the end of the day, you got another answer, and then you find out the difference getting smaller and smaller. So that's why you keep on iterating, and then you get another answer, and then you iterate again, and then they start to converge. And at the end of the day, pretty much like the one that you assume and then the one you calculate is within like a tolerance that's smaller than certain numbers. So certain threshold, and the threshold usually is depends on the spec, or depends on like how close you want to get to. But something like less than 0.05 kips, or maybe 0.1 kips is getting reasonable. So we stop here. So at the end of the day, you see the one that you assume and the one they calculate, they're very close to each other. But so you finish this segments. So this is not the end of the day. Remember, like we have, for the piles that you have 4 different elements for this one. You can divide how many elements you want. If you want accurate, you can like divide it like a thousands, or I think that's what computer code do. Or at some point, like elements n versus n plus 1, like is about the same, give you the answer. Then where is the sweet spot that like the minimum required elements you need. But anyways, you by doing this, you finish the last or the fourth elements. Then you'll be taking the number that you have, right? Because this number now, the top of your fourth elements become the base of the third element. So you can take this number, whatever you have at the end of the day, take this number and then put it from the top again. I'm sorry, like the top, put it at the base again, and then you assume like this part when you start is 0 again. So this was the base, and this is the start. Like you do the whole thing one more time again, and you realize this time you start to be converged much easier. So you do the same procedure, you get this number, and then this will go to your next iterations, and then like at the end of the day you get numbers. I get another like calculated answer at the top of that elements, and the difference converge really quick, pretty much to get the same thing. So pretty much like this may not necessary anymore. But like for Excel spreadsheet or computer program, you just keep the iterations like are constant. But anyways, so you finish your third elements. So this is the third elements. Then you keep up. You can do the same thing again. Your bottoms of the top of the elements becomes the bottom of the next elements. So this number that you get, at the base that you get, sorry, at the top that you get, become the base of the next element again. So same thing here. Like the top of the second elements becomes the base of the first elements. And at the end of the day, when you get to the top of the first elements here, that is the head of the piles. So here is the head of the piles. So that's how you get all the answer. And now at the end of the day, you can plot out the results. So this is what you want to have, the final product. You want to know the settlements at the given loading, and it tells you the displacements along the depth. So this is like elements like number 1, the midpoint, right? The midpoint of the element number 1 is 25 feet, and the midpoint of the second element is 75 feet, third and fourth, so on and so on. Then like for each one of it, you can calculate the settlements of the elements. So pretty much this is the settlements of your elements. And like so this is the settlement of the midpoint of the piles, but this is the settlement of the piles, elastic compressions, and also plus the base. So you will have all this like a settlements there of each segments, and then you can calculate, you can plot out to see how the settlements at different like different depth. So the more the smaller the thickness of each segments, the more number of segments that you have, the more data point that you will have to form this curve. So you fill up the gaps between like those points over there. If you use like instead of 50, maybe 25 25 thickness of each segments, then now we have 8 segments instead of 4 segments. But anyways, like this is how you get the displacement curve from the TZ analysis, and it give you all the number you need, both the elastic compressions, side frictions, and also the base settlements. And here you also this is powerful because this also gives you the side frictions and also the side frictions and also the loading inside the piles. So which are those number there. So this gives you like the average loadings on the piles at different like elements, at different like segments, and also the side frictions of the piles. So pretty much this is the elastic compressions loading, and this is the mobilized side frictions along the piles. And you know the depth of that segment, so that's why you give you a good demonstrations how the axial load. So pretty much this is axial load. The blue is the axial load, and the pink is the mobilized side frictions. So this is like the very simple TZ analysis of a piles. So if you can understand this, I think it's great. I hope like the end of this class at 4000 level push you a little bit to have to kind of like open the box a little, the black box of like the computer that you may use in the future a little bit, and give you an ideas on how advanced geotech analysis is done. So this is the TZ analysis. And